Okay, everybody, let's take a look at a projectile motion question at an angle. A ball was thrown 20 meters per second at a 30-degree angle with a horizontal. So here's 20 meters per second at a 30-degree angle. This is what it would look like laid out. It's important to separate our x and y components because gravity is always influencing this thing. Gravity is making this thing fall down. So we have a negative acceleration along the y, and that's going to be negative 9.81 meters per second squared. That's always happening. So we actually already have some values over here. AY is equal to negative 9.81 meters per second squared. As long as we're playing ball on Earth, we will always be experiencing gravity near Earth's surface at a rate of negative 9.81 meters per second. So let's take a look at the trajectory of this thing. So the ball will follow a trajectory sort of like this. So let's zoom in on this trajectory real quick. So this is kind of what it looks like. Now, initially, there's going to be a y component of that 20 meters per second going up, and there's also going to be an x component of that 20 meters per second going right. Now, that x component all along this projectile's trajectory remains the same because there is no acceleration along the x. So this right motion will always stay the same. So if we zoom back out and let's look at our table. The acceleration along the x is 0 meters per second squared because there's nothing speeding it up or slowing it down if we ignore air resistance. For example, if this was a balloon, no way you'd be able to throw a balloon like this. A balloon would look very different. If you threw a balloon would kind of flop and fall like that. But it's not a balloon, and we are ignoring air resistance. So there is no deceleration, nothing to slow this ball down. Our velocity along the x will remain the same. However, our velocity along the y will get smaller due to gravity. And our velocity along the y final, when we land, is actually the same as the initial, just negative. So important things to consider. Let's actually break up the 20 meters per second at a 30-degree angle into its corresponding x and y values. So to do that, it's important to look at your reference table. To find the y component of any vector, you take the vector a, multiply it by the sine of theta. To find the x component of any vector, you take that vector and multiply the cosine of theta. This follows simple trigonometry. I don't think this video is the best place to get into it. Let's just take a look at the equations and work those things out. Okay. So, velocity along the y is equal to the vector, the initial velocity, times the sine of theta. So the Vy is equal to 20 meters per second times the sine of 30. That will give us a velocity y of, it should be 10 meters per second. Let's see. On, clear. Clear, one. There we go, great. 20 times the sine of 30. Oops. Try that again. Sine of 30. Nope. There we go. Great. 10. Velocity y is 10 meters per second. Great. Let's find the Vx. So the velocity along the x is equal to the velocity times the cosine of theta. So velocity along the x is equal to 20 meters per second times the cosine of 30 degrees. That's going to equal this times the cosine 17. The x is equal to 17.3 meters per second. Let's bring up some of these values up here. Velocity y, the initial velocity, is equal to 10 meters per second. The velocity x is equal to 17.3 meters per second. Also, we know that at the tippity top over here, there is no velocity y. Velocity at y at the halfway point is equal to 0 meters per second, right? This is the halfway point of the trajectory. This is half of the trajectory. So the halfway point of a 0 velocity. Also, the velocity y at the final, when we land, is negative 10 meters per second, right? Because the velocity going up here is the same as the velocity going down here. However, at the end, it's going down, meaning we're going to give it a negative value. Great, so we have a ton of information already, and all we did was break up the initial vector into its x and y components. Now, the first question is looking for us to find the time. What is the hang time? And to find the hang time, you can approach this one of two ways. Now, the simplest way would be consider the whole time in the air. Now, if we're going to do that, we need to look at a few specific values. First, it might help us consider what kind of equation can help us find the hang time. So, we don't have a distance and we don't have a time. So we can't really use the distance equation because we can't use distance to help us find time. Vf squared equals Vi squared plus 2AD gives us distance, not time. This one, fortunately a simple looking equation, lets us utilize two different velocities, initial and final, along with acceleration to find time. We have all of those values. We can use this one. So Vf, let's do number one. Vf is equal to Vi plus At. I'm going to use the final velocity down here. I'm going to use the negative 10 meters per second. Negative 10 meters per second as the final velocity is equal to the initial velocity of 10 meters per second up, plus the negative acceleration of 9.81 meters per second squared times time. Now, minus 10 on both sides to get 9.81 times time by itself. 10 minus 10, as you may know, is 20 or negative 20 meters per second is equal to negative 9.81 meters per second squared times time. Divide by negative 9.81 on both sides. Divide by negative 9.81 meters per second on both sides, and you're going to get 20 divided by negative 9.81, something close to 1, or something close to 2. 20 divided by 9.81 gives us a time of 2.03 seconds. So this is going to be 2.03 seconds. I should say 0.4, I guess, because we can round up. All right, now this is also solvable following a different strategy. So rather than look at the halfway point or the total point, you can look at the halfway point and simply double it, because the first half is the same as the second half. So the time it takes to go up is also the time it takes to fall down. So another strategy would be to use the time it takes to get, or the velocity at the peak to find the time, using the halfway velocity. So to do that, you can use 0 meters per second as the final velocity. That's going to equal the initial velocity of 10 meters per second times At, or negative 9.81 meters per second squared times t. Now let's subtract 10 on both sides. You're going to end up with negative 10 meters per second is equal to negative 9.8 9.81 meters per second squared times t. Divide negative 9.81 on both sides, and you're going to get a time of 10 divided by negative 9.8, or I should just say 9.81, because it's also negative 10. 1.01. That's a different answer. That's kind of weird. But that's the time at the halfway mark. To get the total time, multiply this thing by 2, and you'll find that we're going to get, again, 2.04. Great. So we just looked at a few different ways to solve for number 1, time. Again, time is going to be 2.04 seconds. Great. Now, let's move all of this out of the way. We can scooch it over here to the right for now. Let's find its maximum height. Now for maximum height, we're looking for the dy, which again is constantly changing. At any given point, you're at different heights, right? But we're going to look for the dy max. Really, we're looking at the halfway mark over here. Now, look at the values you have at the halfway mark. There's several different ways you can approach this. You can use this equation if you want. Vf squared is equal to vi squared plus 2ad. You have the velocity at the top. You have the velocity on the way up. And you have acceleration. It's doable. I like this one because the distance is already isolated for you. And we also have all these other values too. So let's try this one. So for this one, we're going to take a look at d equals vit plus 1/2 at squared. So the distance y is equal to the initial velocity up, 10 meters per second, times time, Why isn't it 2.04? Hopefully you know. 2.04 is the total time. I'll show you what that looks like on the calculator shortly. I'll show you the problem with that. In fact, let's save this value on our calculator. I'm going to store this thing as t for now. We'll pull it up later. Store that as t. Anyway, we're not going to use the total time because to get to the peak, to get to this peak up here, 2 seconds didn't go by. The amount of time that occurred was half the time. T1/2, 1.01 seconds. So we're going to use half the time, half of 2.04. Or in this case, what we calculated earlier, I'll just say 1.01 seconds. It's important. In fact, you could solve the same way. Let's finish writing this thing out, and I'll show you a different way you can write this if you prefer. Plus 1/2 negative 9.81 being the acceleration, meters per second squared, times, again, 1.01 seconds squared. You could have written it also this way. dy is equal to 10 meters per second. You could have used the total time, 2.04 seconds, divided by 2, because it's the halfway time, the halfway part, plus 1/2 negative 9.81 meters per second squared. And again, we're going to use the halfway time, so we can take the total time, 0.04 seconds, and divide it by 2 for the halfway time squared. Either of these work. Now, if you punch this into your calculator, I'm going to use this first equation because we've already found half time. 10 times 1.01 plus 0.5 times negative 9.81 times 1.01 squared. That gives us a distance, the dy, of 5.09 meters. Or I'll say 5.1, because if you round it, like 5.1. let's take a look at this other method of solving for this. So I'm going to do 10 meters per second, 10 meters per second times half of the total time, 2.04 divided by 2, plus 0.5 times gravity, negative 9.81, times half the total time, 2.04 divided by 2, squared. And we get essentially the same answer. We also get 5.096. If you round it, it's 5.1. Now, it's very, very key you don't use the total time, because if you do this again with the total time, you're going to find the difference in height from beginning, which was ground level, we threw it at ground level, all the way to the total time, all the way at the end, which is also ground level. So what's the difference between ground level and ground level? Let's find out. 10 times, we stored this as t if you recall, so I'm just going to throw t in there, plus 0.5 times negative 9.81 times, again we store this thing as t squared. 0. Whoa, the difference between ground level and ground level is 0. The total change in height is 0. You can't use the total time. You have to use the half time, a halfway mark. That'll give us a distance of 5.1 meters. You could have also, again, used this equation, vf squared equals vi squared plus 2ad. If you wanted to do that, I'll just set it up quickly. Vf, let's do purple, just to keep in mind we're working on number 2. Vf squared equals vi squared plus 2ad. It would look like this. 0 meters per second squared, because that's the vf at the top, right? The vy here equals 0 meters per second. That's going to equal the vi squared, 10 meters per second squared. It's a 10. Plus 2 times negative 9.81 meters per second squared times d. And if you use this equation, you'll get the same answer that we got earlier. Something close to 5.1 meters. Okay. We just solved number 2. Let's move this stuff out of the way to make some space. Let's bring it down here. And again, the answer for number 2, if we zoom in again, is 5.1 meters. Now, what's the total distance traveled when this thing lands? So if we want to find the total distance, or let's say dx, let's do this in blue, right? We're looking for the dx. What's that equal? Now, you could use the distance equation here. Distance is equal to velocity initial times time plus 1/2 at squared. Now again, we're using x components for this. So the distance x is equal to the velocity x, 17.3 meters per second, times the total time, because we're not looking for the distance at the halfway mark. Total time is going to be 2.04 seconds, plus 1/2 the x acceleration, which is 0, times t squared. It doesn't really matter because 0 is going to delete all of this, cancels it all out for us. So we're just going to basically do 17.3 times 2.04. 17.3. If I can get this thing to work, 17.3 times time, which we stored again as t. Oops, not y. T. There we go. We're going to get a total distance along the x of 35.3 meters. So that's 35. The distance x is 35.3 meters. if you use the halfway time, if you use 1.01, if you use 17, let's do that here. You do 17.3 times 1.01. That's going to give you the distance it took to get halfway across this thing. It'll give you this distance over here. That would be 17.5, let's say, meters. Now, this second half will also be 17.5 meters. Just don't forget, if you're doing the halfway time, to multiply this thing by 2. And again, you should get your answer, something close to 35 meters. So these are all the Regents kinds of questions you'll get. We could find a lot more information. 35.3 meters. We could find more information. I could ask you about any of these values at any point in its trajectory. I could ask you, hey, what's this velocity here? What's the height of this thing here? What's that height? And all you have to do is punch in the different times. You could utilize different velocities. You just have to tweak some of these values that you're inputting into your formulas. But this is typical Regents questions. This is what you should expect. Anything that kind of varies from this is, an intentionally harder question. If you have any more questions, let me know. I'll see you in class. Hope this helps.